Okay, so we'll begin, and on Monday we talked about correlation, and we said the value r can take on any value between -1 and 1, and r tells us about the sign. It tells us the direction and strength of a relationship, right? Okay, so let's start off with a clicker question. Okay, because you guys got here on time, and so we should have that count for something. So let's see. We will say if the x variable represents the okay, so we'll say x represents the number of bedrooms in a house, and y represents the number of closets in the house. Okay, we'll say what is a reasonable value for r? And, okay, we'll assume a linear relationship. Okay, so this is very important that I include this. Okay, so what is a reasonable value for r? Okay, and your answer choices are r is equal to 1, r is around 0.8, c r is around 0.2, d r is let's say -0.5, or e r is equal to -1. Okay, so we'll get the we'll get this going. Again, assume a linear relationship. X will be the number of bedrooms in a house, and y would be the number of closets in the same house here. So you can talk with your neighbor about this. Okay, just a little. I feel it. Okay, well, get your clicks in, and we'll click stop here. Okay, let's see. Let's take a look. Ooh. Now I feel a little guilty. Okay, the answer is going to be B. Okay, a reasonable. Well, I don't know. Maybe should I give you? Okay, because for r to be 1, okay, for r to be equal to 1, this means everything is in a perfect straight line. If you increase the number of bedrooms in the house, we can predict exactly the number of closets in the house. This means there is a direct relationship between bedrooms and closets. So this, only happens if there is a direct relationship between bedrooms and closets. Meaning that this means every single house that has 4 bedrooms has the exact same number of closets, okay? And if that's not the case, R will not be 1, okay? So, that means all houses with 4 bedrooms have the same number of closets, okay? All houses with Okay, and so I think, a strong relationship where the number of bedrooms is positively correlated with the number of closets makes sense, but for it to equal 1, that would mean every single house with 3 bedrooms has the same number of closets, every single house with 2 bedrooms has the same number of closets, and I don't think that's the case. So, so R equal to 1 is not possible there. Okay. Okay, let's talk about finding modeling the relationship between X and Y. Okay, so correlation is able to describe the strength and direction of a relationship, but sometimes we want to go beyond that and we want to model a relationship. Okay, so we may want to create a mathematical model for the relationship between X and Y. So the relationship between X and Y. Okay, and so I think my first example was the length of snakes and the weight of snakes, right? So let's just go back to this example where X will be the length of a snake and Y will be the weight of a snake. Now we may find a strong correlation, okay? And we might find the correlation between X and Y is equal, I don't know, to 0.95. Okay? And so this, and a linear relationship. And there's a linear relationship. So if we create a scatter plot, we see a linear relationship. And so what this means, what we can say so far is something like, if we expect longer snakes to weigh more than shorter snakes. Now, perhaps we want to be more specific than this. Okay? And so in this case, we could create a mathematical model. And with a model, we can, kind of quantify this. Okay? So with a model, we may be able to say if one snake is 1 inch longer than another snake, we expect the snake to weigh, I don't know, I'm making up a number here, 15 grams more than the other snake. Okay. And so this, rather than just saying longer snakes tend to weigh more than shorter snakes, we're actually quantifying what we mean by that. We're saying if one snake is 1 inch longer than another snake, we expect that snake to weigh 15 grams more than the other snake. Something like that, okay? And when we talk about a model, so keep in mind a model, or when we say a mathematical model or statistical model, is a simplified representation of the actual relationship. Okay, if we think about what are the things that go into determining the weight of a snake, there are lots of different factors, right? One of them would be the length of the snake, but other things would be, how recently it has eaten, what kind of diet it has, I don't know, genetic factors in going into determining the weight of a snake. So the true relationship is quite complicated, okay? And to maybe understand the true relationship between the length of a snake and its weight, or the things that determine the weight of a snake, we'd probably have to understand, a lot about snake biology and, all of these things. And it could be quite difficult. And so when we're talking about models here, we are having kind of like toy versions or simplistic versions of the actual relationship. So, knowing that many factors go into determining the weight of a snake, we can just kind of simplify it and say, one of the most important factors is the length of a snake. And if we take into account the length of a snake, we can say something like, if one snake is 1 inch longer than another snake, we expect this snake to weigh 15 grams more than the other. So these are just simplified representation of the actual relationship. So in our course, we cover linear regression. And with linear regression, we create linear models, okay? So we make linear or straight line models between x and y. So I'm going to flip the slide here. And so if you recall from algebra, the equation of a straight line, we often say y is equal to mx plus b. In statistics, for linear regression, the equation of a straight line will be y hat is equal to a plus bx, where a represents our intercept and b represents the slope. Okay, so in statistics we have y hat is equal to a plus bx. The little cap over here, okay? This is called y hat, where hat is the hat. Okay, this is called y hat, and this just means it is not actually y, it is something related to y. So whenever you see a hat over something, it means it's not the actual thing, but something related to it. Okay, so hat is hat means not the actual y. That's something related to y. And so in our case, we're saying this is not the actual value of y, but rather our prediction for y. Okay, so in our case, y hat is not the actual value of y, but our prediction for y. Okay, and because it looks like a line, y hat is equal to a plus bx, what this means is that you might have data okay, so these are the actual pairs of data between x and y. But we are going to make predictions based on a line. And we're going to say, okay, we want to know the equation of this line, okay? So linear regression will get the equation of this line. And the idea here is that if we're given a particular value of x, okay, so if we are given a particular value of x, we just plug it into the equation of the line. The line puts us right here, and this is our prediction for x. Okay, so we say, oh, okay, right here, we go right there, we come over here, and then this is my prediction for y. So right here, this is y hat. Okay, so if we are given a value of x, we plug it into the equation, of the line. And we will get our prediction for y. Okay, our y hats. Prediction for y, which is y hats. Okay. Now, let me just copy this this picture. Yes.
What do we use the term regression?
Why do we call it regression? There's a historical context, and I don't know if I should get into it. But the term regression comes from the first time we did this, it was done by a man named Francis Galton, and he was trying to find a relationship between kind of some genetic things, and he found that despite the predictors indicating that something we would expect it to be higher than normal, it tended to be closer to average than to the extreme. And he called that regressing towards the mean. But that's not the critical part of today's lesson. So, okay, so we've got x here, and let's say we have an actual observed value right here for this particular x. Okay, so we have an actual value. So this here, let me, I'll draw, see that? So this will be an actual data value, okay, data point. So this is an actual data point which will have the coordinates x, y, right? Our prediction puts us right up here, okay? I'm sorry, I really don't know where the static is coming from, but that's okay. So this is an actual data point x, y, this dot right here, and this is our prediction for y given that x. Okay, so this is the spot x, y hat. Okay? So the difference between our prediction and the actual data point, this is known as a residual. So let me see if I can pick a color here. All right. And so this distance right here, this is the, looks exactly the same as red, doesn't it? Is that me? I don't know what's going on. Okay, is that better? No. Okay, so this distance is the residual. Okay, the residual is equal to the difference between the actual value and predicted value. Okay, or we can just say residual. The symbol for residual is E is equal to actual minus predicted, or we will say E is equal to Y minus Y hat. In this case, the actual is below the prediction line, so it has a negative residual. Okay, so this here, if the actual is less than the predicted, the residual is negative, and vice versa. Okay, and so every single data point has a residual. Every data point has a residual. Now, if the data point is directly on the line, the residual is 0, but there's still every data point has a residual. So, you know, we come along and we say, okay, here's this data point, and here's its residual. This data point is very close to the line, so it has a very small residual. This one, you know, has a residual right there. And so we go and we find all the residuals for every data point in our set. This would be the difference between what our regression equation predicted and the actual value that we observed. Okay, so every data point has a residual, and the goal of linear regression is to find the best fit line, and we're going to define the best fit line as the line that minimizes the total squares of the residuals. Okay, so let me just kind of further copy this. Okay, so we got this right here. Let's see if I can. Okay, and so linear regression finds the best fit line. Okay, and we define the best fit line as the line that minimizes the total squares of the residuals. Okay, and so sometimes we call this, because it's minimizing the squares, we might call this the least squares line. So that's another way of calling linear regression what it's called. Sometimes it's called least squares regression. Okay, so this could also be called least squares line. And you'll take a look at this in lab 2. Okay, and in lab 2, you're going to do some linear regression. And basically the idea here is we take each residual and using the length of the residual as the side of a square, so that's supposed to be a square here, we take the residual and we form a square, okay? And we do this for every single residual. So we get a little square here, we're going to get a big square here, okay, and another square here, and here's another square, and there's a square. Okay, so every residual gets a square. Sorry, I'm being obsessive about this. I'm gonna draw squares for every single one. Okay, mission accomplished. So we get, we have squares for every single residual. We square all of them, and we add up the total sum of squares. Okay, so we do this, and if we had a different line, we would get different squared residuals. Okay, so let me. There's actually a little web page, and let's see here. Oh, come on. All right, so this is going to be explained visually, and I want. Oh, all right. Come on. Okay, so here's the these dots are the actual data points. Okay, these are the actual data points, and we can see it takes the difference between this dot and what we predicted for that that x value, which is the line. Okay, and we can adjust, we can change if we change the different intercept, or if we change the slope. Okay, we can see that for different values. So if the prediction line is right here, okay, we can see there is a big residual right here, a big residual right here, and this one has a small residual, and we add up the total squares of those residuals, and we see, okay, this takes up a lot of area, and so we can adjust this, and as we pick different values for the slope and intercept, we can see how the sizes of the residuals and thus the sizes of the squared residuals change. And least squares regression, or linear regression, tries to find the slope and intercept that gives us the minimum value that we can achieve here. Okay? Does this visual work out for you guys? Okay, so I'll put a little screenshot of this. If you are, curious and want to explore this on your own time, here is the web address there. We'll throw this. Now, of course, it gets so small that you can't read it. We'll just screenshot the web address. Okay, and so that's what we're dealing with. Students sometimes ask, why are we dealing with the squares of the residuals and not the absolute values of the residuals, just the distance? And that's because in order to minimize, if you've taken calculus, to minimize a function, we often want to find where the derivatives are equal to 0, and the square function, the quadratic, is differentiable at all points, but absolute value has a non-differentiable point at 0, and so that's why we've gone this route. So we can thank calculus and smart people who figured out the slope and the intercept of the best fit line. Okay, and we can just go straight to the answer without having to derive it, and we can say, for linear regression, the best fit line will always have the following slope and intercept. So the slope, so again, our prediction equation is y hat is equal to a plus b times x. The slope is b, and that will always be r times sy divided by sx, and the intercept, a, is y bar minus b times x bar. Okay. So you can imagine having collected, you know, x and y values, and you've got 10 and 12, 12 and 15 and 9 and 10 or something like this, right? Dot, 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 dot. So x bar is the mean of the x column. Y bar is mean of the y column. X would be the standard deviation of the x column, and sy is the standard deviation of the y column. Okay, so given your numeric variables, all you have to do is you find the mean and standard deviation of your x column, mean and standard deviation of your y column, and then r is the correlation between x and y. You know, with linear regression, we are always trying to use the x variable to make a prediction for the y variable. Okay, so you know, in trying to decide, you know, which one is our x and which one is our y, okay, we always use x to make a prediction for y. Okay, and so the x variable is also called and it might be called the explanatory variable. Let me grab my layout here. Okay, so the x variable can be called the explanatory variable, and if x is called the explanatory variable, then y will be called the response variable. Let's see, x can also be the predictor variable, predictor, and y would be the predicted. Predicted variable. X may also be called the independent variable. And y may be called the dependent variable. Personally, I don't like the usage of the terms independent and dependent variable because I feel like the terms dependent and independent suggest that there's a cause and effect relationship, but that's not necessarily the case. Okay, so we've got, we have all of this. This is all good? And so let's take a look at an example of what linear regression might look like. Okay, and so this is an example from our textbook, and we're going to say, you know, our data comes from, I don't know, a collection of books on the bookshelf. and we will measure two variables. Okay, our two variables. Well, let's see. What we want to do, we want to predict the width of a book. Based on the number of pages. Right? And so, you know, if I draw a little picture, oops, looks something like this. Okay, so here's your book. All right, so maybe this is your stats book or whatever. Okay, and you know, we look at the number of pages, and we're going to look at the width. All right, so in this case, which variable is our x and which variable is the y? We're trying to, yes.
The width is x. Visually there, but then we don't know how many pages there, so
So actually, we want to predict the width. So predicting the width, the thing that we are predicting, this is going to be our y variable. Okay, so the width is y. Okay, y is the width of the book because that is what we are predicting. And the thing that we are using to make the prediction, based on the number of pages, this is the x. Okay, the number of pages, this is our x variable. Okay. Well, let me give you kind of an equation, and then we'll do a quick clicker question here. Okay, so let's say, so based on our data, we find the following regression equation. We're going to say y hat is equal to 6.22 plus 0.0, let's say 0.0366 pages. Okay. And so, or 0.0366 x, or we can say predicted width. So width hat, something related to the width, but not exactly that, is 0.0366 times pages. All right. So if a book has 100 pages, we predict, work quickly here, we predict the width to be what? I'm going to give you some answer choices here. Okay, so A, B, and C, so we'll say 3.66. We'll have 6.2566, 9.8. 586. Okay, so we'll go ahead and run that. It should be open. Should be open. Stats. When you click. All right. So this should be an easy question. Okay, I'm gonna go ahead and close out the poll. So if you haven't put in your clicks, get your clicks in. All right, let's take a look here. Okay, yeah, that is correct. So all you have to do is, given a regression equation, you just plug in the value. So in this case, if we have 100 pages, our y hat is going to be 6.22 plus 0.0366 times 100. And when you do this, you get 9.88. Okay, so our predicted width is 9.88. Okay, and it's very important that we use the word we predict the width, because this does not mean that every single book that has 100 pages is exactly 9.88 millimeters. You can have several books that are all 100 pages but have different widths. We're just saying, based on our data, if a book has 100 pages, this is what we predict the width to be. Okay, let's just try this out. So we have predicted width, okay, and we'll say a number of pages. So we said if we had 100 pages, we predict the width to be 9.88. Okay, so just quickly go ahead and try out what is the predicted width for 200 and for 300 pages. So we have y hat is equal to 6.22 plus 0.0366 times pages. Okay, so our y hat predicted width, number of pages, this would be our x. Okay. Okay. Do we have a value for each of these things? What do we have? For 200 pages, we predict the width to be 13.54, yes? Okay, and then what do we predict for 300 pages? 17.2. Everybody's good there? Okay, so here's my question. How much did your prediction change when you went from 100 to 200 pages? When going from 100 to 200. Okay, so this number increased by how much? It went up by 3.66. Okay, and what about from 200 to 300 pages? Okay, the difference there is also 3.66. Yeah. Okay, so if somehow the multiplication button on your calculator broke and you could only do addition, what would you, could you still make a prediction for 400 pages? What would you do? Yeah, you would do 17.2 plus 3.66, right? You guys, I think you see the pattern, right? And you get 20.86, yeah? Okay, where is this number 3.66 coming from? Yeah, it's coming from this value right here, the slope of the regression line. Right here, this is our slope, this is our b, yeah? And so our slope, what we're saying is that when we increase the number of pages in our book by 100, so we can say something like, if one book has 100 pages more than another book, we predict the width to go up 3.66 millimeters. Okay, I guess if I said that it was being measured in millimeters, but this is what we're measuring. So in other words, what if one book had only one more page than another book? Instead of going up 3.66 millimeters, we would divide this by 100, or we would just go up by this very small value of 0.0366, right? So another way, if we look at the slope is equal to 0.0366, and we would say something along the lines of, if one book has one more page than another, okay, our prediction is 0.0366, which is kind of the slope, value of the slope, more than the other book. Yes, question?
So by definition of linear regression, the best fit line, we just know that 3.66 is not perfect, but it should take into account varying types of paper and publisher book. So is that the line regression?
The linear regression just simplifies everything and just says if we're trying to predict the width of a book based on the number of pages, this is the relationship that we've come up with, okay? So based on the data that we've collected. So, you know, we'll continue our discussion on linear regression on Friday, so we will see you then.